Okay, I hope that you can see clearly the PowerPoint slide. So this is the question that we have to answer regarding on the unit cells, such as like what is the basic structural parameters? Okay, like this constant outside of the cubes, and atom per unit cells. Okay, how many? Okay, what is the volume per unit cell? What is the atomic packing factor? What is the close pack directions, coordination number, linear density, and also planar density. Okay, so I think for today we will cover just about the coordination number and atomic packing factor items. Okay, so what is the coordination number? So if we look at here, that the coordination number is the number of the neighbors. Okay, so for the simple cubic, if you look at here, that the neighbors for the simple cubic atom is 6. Why we say the 6? If you look at here, if we choose the center of the cubic, okay, this atom is touched with their neighbors, okay, meaning that one atom directly touch 6 atom, 6 other atoms, okay, okay, so this atom, 1, 2, 3, 1, 2, 3, 4, 5, and 6. Okay, so this is touch. Okay, this one is not touch, right? This direction is not touch. Okay, so meaning that the coordination number is for the simple cubic is 6. Okay, this is 1 unit cells, 1 unit cells, 1 unit cell. Okay, for the cubic structure. Okay, so how to count number of atom per unit cell? Okay, so you have to remember when we want to calculate the atomic packing factor. Okay, so we have to remember how many atoms per unit cell, especially at the corner, edge, face, or body. Okay, for examples, for the corner, okay, there's the corner atom is shared by 8 cells. Okay, so meaning that in order to get the 1 atoms, we need 8 times with 1 8 to get one atom. Okay, similarly also for edge is for face. Of face, I think is this side. Okay, so there's a half. Since if there's another cubic here, okay, you share with another cube, right? So when you cut here, this become half. Okay, this one also is become half. Okay, so when you combine this face, okay, atom at the face, so it's become one atom, meaning that 2 cells equal to half. Okay, for 1 unit cells, okay, at the face. Okay, and then for the body is a center. Yeah, center is meaning there is a full atom. Okay, so equal to 1 atom per unit cell. So how many atom per cell for the body center cubic and face center cubic? So this is how we want to calculate how many atoms, and then how many how about the void? How many percent is occupied by the matter? Okay, this is what we gonna calculate. Okay, so for the simple cubic unit cells, okay, only polonium has this structure. Okay, so only polonium. Number of atom per unit cell is equal to 1. Okay, coordination number of course is 6, right? Is attached at 6 neighbors. Okay, so this one, 1, 2, 3, 4, 5, 6. Okay, volume per unit atoms. Okay, if you look at here, 4 divided by 3 pi r power of 3. Okay, so this is how we calculate atomic packing factor later. Okay, we need use this volume atom per unit cell divide by volume of the unit cell. Okay, so atomic packing factor, if you look at here, that is 0.52. So meaning that 52% of the fraction is occupied by the fraction of the volume occupied by the matter. 52%, only 52%. Okay, and the rest is a void or is a space. Okay, empty space. Okay, and then closed spec direction is equal to directions where atoms are continuous contact along the cube edge. Okay, let's see this video. I think. Oh no no. Let me share this one. Wait, cubic close sphere. I don't know which one. What is the title? The properties. Let me check. Packing of sphere. Packing of sphere. Oh, this one. Share this one. Packing of sphere for the simple cubic. Oh, I cannot play this one. There's no adopt flash player. Yeah, later I will share later. Maybe I put in the e-learnings or I will share during the next class. I think my adopt flash player is expired the license. I think. Let me check other apps. How about the QuickTime Player? So not possible. It's okay. Okay. So let's see this video. I hope this one we can play. Simple cubic unit cell. Cubic unit cell 6. Is it can be open or not? Wait, for this video. Okay, this one. Share. Actually, I'm at home. Work from home actually, so it's quite difficult because I'm using only one laptop. Okay, another one I have a similar. Okay, can you see this one, this video? Let's see for the cubic unit cells. Okay, you see this video, right? Hope that you can see now this video. This is a cubic unit cell. Okay, simple cubic unit cells. Okay, you cut because you share this atom, right? So how many? This one. This is all the unit cells. So this is one unit cell. What unit cell is have? 1, 2, 3, 4, 5, 6, 7, 8. One particle per unit cell. One atom. Okay, so please remember for uh, uh, 4 simple cubic, okay, for the simple cubics, 1 atom per unit cells. Coordination number is equal to 6. Okay, 1 atom unit cells. Okay, we have a 6 coordination. This is another one showing that for each unit cell. See, that is the void or the space. Okay, when we can determine by using, we can calculate by using atomic packing factor. Okay, equation. Okay, so this is for 1 unit cell. Yeah, simple cubic equal to 1 atom unit cell. Okay, so that is the value. Okay, so I hope that you can understand this one for the simple cubic. Uh, okay, so how to calculate the atomic packing factor number? How we can get the 52%, which is occupied by the metal, right? So please remember this one. Okay, atomic packing factor. Okay, volume of the atom inside unit cell, meaning that this is the volume times with the how many atoms for the simple cubic. Okay, since we calculate is equal to 1, right, for this one. This is a corner side, corner have 8 corners, so it's equal to 1 divided by 8 times with 8 equal to 1 atom unit cells. Okay, so divide by volume of the unit cells, meaning that volumes for the cube, this one A, this one is A. Okay, and this one is A. Okay, A times A times A. Okay, so it's equal to A power of 3. So volume of atom unit cells, okay, inside the unit cells divided by volume of the unit cells is equal to 0.5. So this one you just because just cancel out, so you can get 0.52. So is volume fraction of subjects occupied by the metal. So meaning that another 48% is only the space of void. Okay. So closed direction is along cube H. Okay, this one. Okay, contains 1 atom per unit cell. So please remember for the simple cubic is equal to 52% atomic packing factor or 0.552. Okay. How about body center cubic? Okay, body center cubic. Okay, so let's see for the body center cubic. This one atom unit cells, volume atoms, volume unit cell. Volume atoms, this one is volume is in sphere, okay? 4 divided by 3 pi r power of 3 lah. Okay, since the radius, if you look at here, this is the radius, right? Okay, a power of 3 lah. Like this one. The diameter, not radius. Okay. So A equal to 2R. This one is the diameter. Okay, diameter. This one radius. Okay, if half of the diameter is radius. Okay, so for the BCC, okay, is represented as one atom at each corner of cube and one at the center of cube. So how many atoms? Okay, how volume? How many? How about the atoms per unit cells? How many atoms per unit cells, right? For the body center cubic. Okay. Each atom has 8 neighbors because they have a center there. Okay, the atom at the center. Therefore, the coordination number is equal to 8. Okay. For example, if you look at here, that the radius of or the length of the atoms for each atoms, if you look at here that A is equal to 0.289 for the chromium, iron, sodium. This is have a body center cubic. Okay. Okay. So for the each unit cells, okay, if you look at here that coordination 1, 2, 3. This is the coordination number, okay? This one. This is the center, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So meaning that 1 divided by 8 times 8 equal to 1. Plus this one full atom plus 1. So equal to 2. 2 atoms per unit cell. Okay. Therefore, each unit cell has 2 atoms. Okay, this one full. This one at the corner, right? All at the corner. Okay. How about A is the lattice constant? Oh, sorry, lattice constant or the radius. Okay. So if you look at here that I have to leave this one first. Okay, if you look at here that if we want to calculate, okay, this is equal to A, this one equal to A, this one equal to A. Okay, because we want to calculate this length. If you still remember the trigonometry equations. Okay, so and then from this one and this one, okay, since this is 2A, square root 2A, so we calculate this is A, this one, right? This one is 2A. Okay, so you can get this one equal to this is equal to 4R, right? Because this one is 1R, 2R, 3R, 4R. So if you calculate this one is you can get 3A lah. Okay, so meaning that to get the value of A, so meaning that 3A is equal to 4R. Okay, just bring it to the right side so you can get value of R expressed in term of 4R divided by 3 lah. Okay, square root. Okay, so that's why we can get this one value of A. What this one? Locality is solved. Wait, stop sharing. I reshare again. Okay. Okay. So let's see how about the atomic packing factor number. Okay. If you look at here that a volume of atom unit in cells. Okay. Divide the volume of unit cells. So volume of unit cells is 3 because it's 1 divided by 3. And this one is equal to 2 atoms times with the volume of the sphere. Okay, so that we can get 8.378 R, and this one 12. So just cancel out this R power of 3 to get 0.68. So meaning that is the void is reduced because there's a atom at the center. Okay, so about 68% uh, of the fractions or the void is occupied by the metal. Okay, so this is for the atomic packing factor for BCC. Okay, so let's see this video. Okay, for the BCC. Cubic unit cell 7, cubic unit cell 7. Let me share. Cubic unit cell 7. Video. Okay. Okay, let's see this one, BCC. Okay. I hope that you can see this video. Okay, Scott. Okay, that's one. 2 particles per unit cell. Coordination number is 8. Okay. See? There's a center here. 2 equal to 2 lah. Okay. Okay. So that is the video. So this one is for BCC. How about FCC? Okay, FCC. Let's see. So okay, yes. Later I can send in the e-learnings. Sorry, that's why because I online from my house, right? So I have to work from home just for today's today and tomorrow. That the lattice constant got any other meaning besides side of the cube? Lattice constant is a interaxial angle. So if you refer back my previous slide about the unit cell, the title. Okay, that is lattice constant. So this one I think for the side of the cube is we call it as angular length lah, axial length lah, or more accurate what we can define lah, axial length. Okay, rather than lattice, because lattice constant is interaxial angles and also axial length. Okay. Okay. Let's see the BCC. Okay. Represent third as one atom each at the corner of cube and at the center of the each cube face. Because that's why we call it as face center cubic. There's a atom, right, at the each cube of face. Okay, and FCC the coordination is equal to 12. Okay, and atomic packing factor is become 74 because they have an additional atom at the face air. Okay, so meaning that is the void is become reduced. Okay, so the example is like aluminums, okay, and golds. Okay, that is the examples. Okay, here that why we say that is a 12. no, why we say is how many atoms? Oh, this one, yeah, this one is the face, face. This one is the face. This one is the face. This one lah. 1, 2, 3. At the bottom another one. So meaning that this one and this one is become one atom. This one and the bottom become one atom. 1, 2, 3. 1, 2. What else? Corner. Oh, face 1, 2, 1, 2. Oh, sorry. At the face we have a 6. Okay, 1, 2, 3. This one, another one. Yeah. And then this face, sorry, should be 6. Top and bottom become one atom. This side and this side, this side, right, is become one atom. This side and that side is become one atom. 1, 2, 3. Okay, so meaning that 3 atoms lah. So and then corner another one atom. So become 4 atoms for unit cells. Okay. Coordination number you have to remember is equal to pair. Okay, later we see the video. If atom contact each other across cubic face diagonals. This one, okay, across. Okay. If for the simple cubic is along with the along the cube edge, right? Okay. And then for the BCC, if you still remember BCC, this one diagonal, face diagonal. So if BCC is along along the cube diagonals, meaning that is to this direction. If you still remember just now, because there's an atom here, this one atom and this one atom are to this direction, diagonal. Okay. Okay. So therefore A lattice constants or axial length lah. So 4r divided by square root 2. Okay, this one. So I know you can calculate based on the face diagonals. This one is A, this one is A. So this one is square root A lah. Square root 2A, sorry. Square root 2A. Okay, so equal to 4r. Because this one radius, 2 radius, 3r, 4r. Okay, equal to 4r. So you can get this equation. Okay. Okay, let's see video for the face center cubic. I hope that you can see this one. But later I will share again at in the e-learning. Okay, number 8. So number 8 lah. Okay, so just see first. Okay, first center cubic unit cell. Yeah, this one 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Yes, 4 particles per unit cell. Okay, let's see the coordination number. I think. That one. 1. So it's touch how many? No, 4. Another 4, 8 is equal to 12. So total is 12. Okay, the coordination number. So there's a void. So it's become it's like a slip, right? So the void is become reduced for the FCC compared with the BCC and SC. Yeah, face center cube. Okay. Okay. Later we do tutorial. Calculate. Okay. This one. So geometry along prospect direction, face diagonal related to A, lattice constant and also R. Okay. So this one I already show you how to calculate the lattice constants, right? Okay. So equal to 4R. So volume for the atomic vectors is 4 divided by 3, right? So this is 4 unit atom cells. This is the volumes. This one is A. Okay, volume atoms. And divide by A. So you can get 74%. Okay, 74% we fill with the method. And 26% is voids or space lah, empty space. Okay, so I don't know this one we can play or not. Wait, that can play. This one is the what is the hyperlink? Crystal voice. Crystal voice. Okay. Just like a simple quiz, I think. Can play or not? Oh, cannot lah. This one I cannot play. The same. We need the flash player. It's okay. I cannot play this one. Okay, we do some tutorials lah. Okay. So I give you link for the Jamboard, I think. Let me check. Okay, can you answer? Iron has 20 degree C is a body centered. Okay. BCC with the atom of the atomic radius is 0.124. Calculate the lattice constants A for the cube H of the iron unit cells. Okay, calculate the lattice constant A. So how can you calculate for the BCC? BCC, if you still remember, okay, just refer back the equation for the BCC. If you look at here, that the equation for the lattice constants A, this one, 4R divided by square root 3. Okay, so just use this equation, okay, to calculate the lattice constant. So meaning that A equal to 4R divided by square root 3. Okay, so just substitute into this one. So please calculate A equal to what? Can you calculate? Give me the answer. 0.286. Okay, that's the answer. Okay, so can you do the tutorial one? Tutorials ones, molybdenum at 20 degrees C, body centicubic, atomic radius is 0.14, calculate the lattice constant. The same like a previous one. Please calculate. What is the answer? What is the answer? Just substitute just now. What is it? The value of the previous one for the what's this? Iron, right? Just using this one 0140. What's the answer? And similarly, also please do for the gold 0.40788 and verify the atomic vacuum factor structure is 0.74 for the FCC. Okay, please do this one and I give you link for the Jamboard, I think. But my computer is very slow. So, so okay, please calculate. use the Jamboard lah. Please calculate. Or you can paste your answer in the chat box lah. Can 323. Yes, 323 nanometer. 232. Yes, molybdenum also you have to calculate. 232 0.1442. That's correct. 232. Okay, 233. The answer is here. Okay. For FCC, right? This one, 0.74. This is the answer. Okay, you can use this one. So you already have the answer all. Okay. Okay, any question about the coordination number, atomic vacuum factor, the lattice constants? Any questions? This one, maybe. Any questions? So far, okay. Okay. So far, it's okay. Right? Easy, right? Okay, so let me introduce about the direction indices. I think we still have a time of about 10 minutes. What is the direction indices? And I think for the Miller indices is we will do tomorrow, right? 8:30 o'clock, okay? Okay. Okay, so I thought actually is the direction indices is want to locate the electrons or what is the directions, okay? So by using the Cartesian coordinates, okay? So we can see we can determine or we can locate the atom position in the cubic unit cells. Okay, so just want to share you. There's the three directions, x, y, and z, three axes. Okay, so the position you have to remember. This one. So this one is plus z. Okay, this one is minus x. Minus x, okay, that direction. This direction. This direction. This one is plus x. Okay, this one is plus y. This one is a negative z. This one is negative y. Okay. So the position for the Cartesian coordinate, if you look at here, that this is a 0, 0, 0, 1. Okay. This one is a 0, 0, comma here. 1. Okay. This one is 0, 1. This one is negative 1, 0, 0. Okay, this one 1, 0, 0. This one is 0, negative 1, 0. Okay, so you have to remember this one. Okay, the basic. This is the origin. 0, 0. Oh, so 0, the origin. Okay, this is the origin. So please remember this direction. Okay, this should be positive. Okay, x, not this one positive, and this one y on the right side. Okay, out of the plane, or this one is positive. This one is upper side positive. Okay. Okay. We can locate atom by using a Cartesian coordinate system in a cubic unit cells. Y-axis is the direction to the right. X-axis are coming out of the paper. That one I told you, coming out of the paper, this direction, right? This direction. Please remember. And then what Z is the direction toward to the top lah, on the upper side. Okay. So we can locate by using unit distance along the axis. Okay. All the axis we can locate the atom position lah. Okay. So direction indices is actually is a vector components. Vector components we can calculate. Okay. Resolve along each axis reduced to the smallest integer. What do you mean by smallest Can you hear my voice? Hello? Okay, sorry. I have a problem with the internet connection, so it's already 10 o'clock. But it's okay. Tomorrow we continue on the direction indices, the procedure, and also we will finish by tomorrow lah. If my internet is no, it's okay. This is the problem when I work from home. Okay. So tomorrow by 8:30, okay? So thank you very much and sorry for the with something's a problem, right? Okay, thank you very much. Okay, see you again.